Gail Moore with Teaching One More, and today I'm meeting with Virginia Bastable, who was the Executive Director of the Math Leadership Program at Mount Holyoke. And so we're going to talk a little bit about the work she's been doing around mathematics and algebra and learn a little bit more about math today. Hi, how are you?
I'm really good. I'm so happy to be here.
I am too. I'm so glad you could make it. Good. So I want to hear all about what you've been working on and what, as teachers, we can grow from.
Wow, that's a big
that's
question.
a big question. Okay. So,
I worked for most of my life in Massachusetts. So all of the work that I've done in these books, which I'll talk about in a little bit, is based on teachers writing that worked with us in various projects.
Okay.
And so one of the things that I just want to say up front is that if it weren't for so many dedicated, interested, exciting teachers, I wouldn't have any work to be talking about. All of the work that I do, the books that we produce, are based on teachers writing about bringing ideas to their own students, and the hard work that takes and what they figured out in the process. And so as staff of these projects, we ended up learning so much from the teachers that we could gather their material into books so that other teachers could learn from them. But we're sort of the conduit. It's really a very teacher-driven work.
I'm so glad you said that, because I really think that it's one thing to talk about a theory and have an idea, and then it's another thing to go into a classroom with so many little bodies and personalities and put it into practice.
Right.
Good. So I want to hear more about
So
this.
teachers have really hard jobs. They have, and they have many things pushing on them, and some of those things are actually contradictory.
Okay.
And so I want to go back and talk a little bit about my own self. I was a middle school and high school math teacher for beginning of my career before I got involved in math research and professional development for teachers. And so I know what it's like to go through that change of shifting your thinking from a teacher being someone who is supposed to be a careful explainer to someone who listens to their students' ideas and uses their knowledge of math not by telling the students how to do the problem, but by analyzing the thinking of the students and helping them move further in their own thinking. And that's a big shift that we're asking of teachers.
And that's very rigorous work.
It is rigorous work, and it requires a lot of mathematical understanding.
It does. So it takes some mathematical understanding. I think you have to be very aware of your students and tuned in to who they are and what they're saying,
Absolutely.
right? So how do you get teachers prepared for that type of work?
So one of the things that we do, that I know a lot of teachers are doing out here in California, as someone who grew up in the math world in the eastern part of the country, it's taking me a little while to learn, now that I'm in this new environment, what's happening out here. But one of the things that we capitalize on are the math talks that people are being encouraged to do, where people have, for sort of a brief time, rather than thinking of a whole hour of math or 40 minutes of math, whatever your system allows, but a brief time in which the teacher isn't telling the students how to solve the problems, but rather posing problems and saying, what do you think?
Right.
How might you do this? What do you notice by looking at this equation? And so those are questions and prompts like, what do you notice, that allow every student access. They can all say something. And so sometimes we'll suggest a teacher pose something like 19 plus 6 equals 20 plus 5. What do you notice? And so it's a little different than a number string or a math talk where the point is to figure out multiple solutions or approaches to a problem. But that as students look at that, some of them might just say, some of the numbers are odd, some of them are even.
Right.
I mean, everybody has something to offer. And so when you collect all of the things the class has to say, then the teacher can look at those statements along with the class and decide which ones they're going to pursue. So somebody might say it makes the addition easier because 19 plus 6 might look hard, but 20 plus 5 is 25.
Okay.
And so other people might say you move one from one number and put it on another. And so once you get those kinds of statements up there, then the question can become, do you think that'll work on another problem?
Okay.
And so one of the things that we suggest is that people think about these opportunities for whether you call them math talks or number strings, but to think about how can you build from one to the other so that maybe a couple of days people are doing this sort of what do you notice, and then maybe 2 days later they turn it into, can we write a sentence that says what we think is happening in this example?
So let me stop you a minute because I want to just take it from a classroom teacher's perspective. So my first thought while you were explaining this was a teacher might say, why would I bother to do this? Like, what's the purpose of it, right? I feel like teachers are very sort of answer-driven. Not all, but some. And so but what I'm hearing you say is that when you put up an equation and you ask kids to notice it, you're going to hear some things, right?
Right.
So we're talking about sort of analyzing that student thinking. Some kids might notice even and odd, where some kids might notice I rounded, or it's close to, or you just took one from the other. And so what you're saying is that you can dig into deeper mathematical ideas by posing these equations or problems, listening to your students, and then deciding what's going to give you maybe the best bang for your buck.
Right.
All right. Okay.
Well, that's a great summary.
Okay. I just want to make sure that's clear. Okay.
I appreciate that. Because there's multiple things.
Right.
One thing is helping teachers and students find out that they have mathematical ideas. And so by posing a question like that, a teacher who might be surprised by some of the things their students notice, that their students might notice things they themselves didn't think of, or that they hadn't planned on coming out of the conversation. And so one goal for this kind of activity is to encourage both teachers and students to become aware of their own capabilities as mathematical thinkers. One of the sad things about the way math has been taught in this country for so long is that most of the teachers themselves have not had opportunities to learn math this way.
I would agree.
And I know in much of our professional development, teacher after teacher will say, oh my God, I never even realized what I was capable of thinking. I thought because I didn't understand the traditional method and I just had to fall back and memorize it, that it meant I wasn't good enough. Instead of realizing it was a set of experiences that they had that wasn't adequate to help them.
I could testify to that. I really can. So maybe the way we could reframe it is that maybe I just didn't understand the way it was explained, rather than not understanding math, right? So here's my teacher giving this explanation, maybe not.
And the message we often get is that if you have to think hard about something, it means that you're not smart. When it's really just the opposite. That really digging into a problem and trying to understand it is hard work. It's well worth it, but it's hard work. And unfortunately, we have this image that doing math means reading a problem and saying the answer as quickly as possible. And
that was what was valued, right? That was my own experience. Whoever was the fastest was the smartest, was the best.
Right. And so people who tended to be analytical or think about things or wonder were made to feel poorer students rather than offering a rich source of examinations. I want to tell a story. This is a story about my two kids, actually, which has nothing to do with math, but like any teacher, anytime you're in a place where you're watching learning take place, you're sort of paying attention to it. So when my son was taking swimming lessons, now my son was a 5-year-old energetic kid, and he loved the water. but he wasn't so much under control.
Sure.
And to him, the point of water was jumping and splashing and having fun, and it is. But in order to learn to swim, he had to learn new skills. And so his instructor was saying, when you kick, you don't want to make splashes. And so he kept trying to control my son's behavior by saying, you don't want to make splashes, you don't want to make splashes. And really, that's what my son wanted to do. Eventually, my son learned how to swim and came to peace with this. But I noticed a few years later when my daughter was having swimming lessons, that the instructor told them that the point of kicking is to move yourself forward. That's where your power comes from.
Okay.
And that when you kick like this, you move yourself forward in the water. That's how you get to swim faster. And you can tell when you're kicking in the water by not splashing. Because when you kick in the air, you make splashes, and that energy is wasted. It doesn't move you forward. And I remember thinking, what different messages my two kids got about swimming. For my son, it was about controlling his behavior. And for my daughter, it was understanding how it worked. So she would choose not to splash because she wanted to swim fast. But what my son got was sort of like the rules of the algorithms. Put these numbers here, mark them here, write them here, and the right answer shows up.
Yes.
It was about behavior, being neat, remembering the rules.
Right.
It wasn't about how mathematics really works.
Yes.
And I love that story because it's like it's fun to understand how mathematics really works.
It is.
It's very accessible, but we have this image that first we have to learn all the rules, and then later on we can learn what's really going on. And I think that's wrong.
And I think it's hard to get past all of those rules sometimes that don't necessarily make sense.
Right.
When they're not attached to purpose or meaning.
Right.
It's funny you should say this though. I love it because the other day I was working in a school and teachers were showing me the curriculum that they were working on and the problems kids were solving. And I thought to myself, it's so early in the school year and it seems like you're teaching number procedures versus number sense.
Right.
Right? And I think teachers look at that place value chart, ones, tens, hundreds, thousands, and they say I'm teaching place value. But what I really feel like it's teaching is place position, right? Not really what's happening underneath.
Right. Like if you ask kids with a big number, like, let's say, I don't want to make it too big so we can hold it in our head, but if we have 24,325, and we say how many hundreds are in that, people will say 3.
Yes.
And there are not 3 hundreds in 24,325. The 3 is in the hundreds digit. That is absolutely true. The digit 3 is in the hundreds place, as you said. But we mix up that idea about how many hundreds because you're losing the value of the actual number by paying individual attention to each digit and not thinking of the number as a whole.
Right. I think that standard algorithm where we're lining up the numbers really limits kids' ability to understand number sense and how many hundreds and tens actually are in a number.
And we are actually inconsistent in what we say. Like we say you can't have more than 9 in a digit. But then when we teach the subtraction algorithm, we tell them to cross off and put a little 1, and they're making a 13 right there. That's what they're doing, and for good reason.
All these rules.
Yeah, and so I think for a lot of people that may not feel like they understand math, it's because they notice these inconsistencies, and it bugs them, and they think there's just something wrong with them instead of something wrong with the system that they've been experiencing.
So I'm so glad about the work that you're doing because you're working to correct those inconsistencies, right? So tell me a little bit about your book, Connecting Arithmetic to Algebra.
Well, this is the first book that we wrote in this sequence.
Okay.
And it was designed to help people think about, if actually the cover has one of our main problems on it. It has showing how 6 can be 1 plus 5, 2 plus 4, 3 plus 3. And this is an activity a lot of teachers do, but it doesn't go any further.
Okay, say more about
And
that.
so one thing that we want, and so I'm going to actually move to the other book,
Sure.
because the second book we did builds on this one, but offers some different kind of opportunities. So this one is about why does it work, and they're both from Heinemann. And one of the things that happened is that the teachers we were working with as we wrote the Connecting Arithmetic to Algebra participated in a project with us where we would do math with them, we would pose these same ideas with them, and then suggest they pose these questions to their students and write about what happened. And then they'd come together and read each other's writing, and the staff would read the writing, and we would use that to build the book. And in the middle of that process, a lot of the teachers said, we really get what you want us to do. We're beginning to understand what our kids can do. They're capable of more thinking about this. But our knowledge of mathematics isn't as rich as yours. And so could you give us some sample lessons that we could use? And those sample lessons ended up being in this book.
That's awesome.
We wrote them for the purpose of research.
Yes.
In order to help the teachers we were working with have consistent experiences.
Okay.
Instead, so if 3 or all the 3rd and 4th grade teachers were working on the same set of ideas, then they could share better and grow and use each other's ideas better. So we ended up writing lesson sequences that could be done in 10 or 15 minutes, a couple of times a week, over a long period of time. That our teachers were telling us that the students were really engaged in these conversations, but that they were intense in a different way than the regular math class they were running.
Oh, say more.
And so they found having students attend to something for 15 minutes meant that they could control the attention span, they
Sure.
could keep track of it, and they also found that that meant that they would have a couple of days to look at the result of what they called their algebra improve sessions.
Okay.
And so they might spend 2 or 3 or 4 days doing one of the noticing activities. And then at the end of that time, the teachers would have all the chart paper, the result of the student work, and could then look at that to decide, now we're going to move into articulating as the next phase of our work. And so they could look at the student work and bring back to the students, here is where we left off. Here were 2 or 3 sentences that people said, let's make a class conjecture that we can work on. And then they'd spend 2 or 3 of these 10, 15-minute sessions doing that until they come up with a class articulation they felt was satisfactory.
I love that, really digging deep into an idea and revisiting something. So it's not like we just did it one day and it goes away.
Right.
They sort of serve as sort of anchor charts.
But it also meant that they're still doing something 15, 20 minutes a day, but it keeps building.
Yes.
So after articulating, they end up then doing what I think was probably the most misunderstood section, and that is using representations to make sense of the articulation.
Okay.
That is, can you draw a picture? Can you tell a story? Can you use the cues to show what's happening with your articulation? So maybe they've got an articulation that says, if you add 1 to one add end and take it off the other one, the sum is the same.
Okay.
Which is an articulation of the example we started with. So they might use cubes to show that if you're adding 5 to 4,
Yes.
that if you take 1 off the 5, well, this is kind of a silly example, because if you take 1 off the 5 and turn it into the 4, we're really showing the commutative property.
I don't think that's a silly example.
But then if you take 1 more off, and so by using the cubes, you can sort of see, the total is remaining the same even as the add-ins shift.
Yes.
And then even though there is a specific number of cubes in my hands, we've seen lots of kids who sort of say, well, it really doesn't matter how many I have in this hand and how many I have in this hand. If I take one and move it to the other hand, I have the same amount.
Okay, so I want to pause you because I feel like you said a lot there. So the first thing I'm hearing is that you're showing them perhaps equations and asking them what they notice, right? Maybe a few of those for a couple of days,
Right.
and then we're articulating what we see,
Right.
right? So we're making some connections there, and then you end with a representation, perhaps with cubes or pictures.
Well, it's not actually the end.
Okay.
It's sort of the middle.
Okay, so before we go there though, but I love the idea of connecting all of these ideas rather than just letting each sit in isolation.
Yes.
Okay, so
That's absolutely, and there's all kinds of intermediate stages. So
Okay.
another kind of question we might ask during the noticing activities. I mean, so it's sort of like this whole group of things that might be under the noticing is you might ask kids to generate equations of their own that work the same way.
Right.
And then you have a whole wall of
Oh,
things
that's
to
fun.
look at, including, do they come up with things that actually aren't true? I mean, what are they really thinking of the same rule or
Okay.
not? And so by giving them the opportunity to
Put it
generate
into
a
practice,
bunch, and then the
right.
whole class can look and say,
Mhm.
which of these still fit our rule and
Mhm.
which don't?
Mm-hmm.
So that's another component of noticing. So so far I've talked a little bit about noticing, a little bit about articulation,
Yes.
which we find actually is best as a collaborative group activity, that the whole class as a whole can generate a better conjecture in terms of the wording
Sure.
than individuals.
Sure,
The individuals
sure.
start and then you put them up and then the whole class sort of hones it and drafts it. We have lots of teachers who do these in different colors so that they might start with a green one and then as students offer different wording, they might rewrite it, they might replace it with red or then yellow so that you have a whole history of where the class started and where they are.
I love that. I love that whole group articulation, especially here in California, a large English language learner
Right.
population, so we're supporting one another
Absolutely.
and collaborating. But you even made a connection to writing,
Yes.
right? Stating a claim and then revising over time
Yeah.
and like recording those ideas. I love that.
Well, actually, there's a lot of, this is sort of a byline
Sure.
to this main story I'm telling, but there's a lot of connections
Mhm.
with writing. And so, for instance, we often don't make connections with a complicated math problem and a writing, thinking of our first solution as a draft.
Okay.
And
Okay.
where if you think originally, if it's a big, complicated kind of problem, then your first attempts are like a draft.
Sure.
And we know from the writing process a good thing to do next is to have some of your peers look at your draft
Mhm.
and then help you revise it. And then go back and think about, okay, now that they've pointed out what makes sense, and that's all part of the Math Practice 3, sort of critiquing the work of others, sort of using the students' ideas to help other students revise their. So it's a different connection to
But
the writing process, but
they
one
are
that
connected.
isn't usually understood.
No, but it's interesting though, because to go back to what we were first talking about when we started this conversation, if you're posing a problem to your class and students are answering it, 2,
Right.
3, 5 seconds, was it really challenging?
Right.
Right? Whereas if you're posing a problem and they have to grapple with it a little bit and maybe create a couple drafts, you know that you're giving them some work that's at their just right level, or at least pushing their.
There's an opportunity for learning.
Yes.
If there's, I think we too often mix up learning with just knowing.
Yeah. Oh yeah.
Knowing is the result of
Mhm.
learning, but it isn't the same thing.
No.
And so when people make those silly comments like, I don't want someone building a bridge that is still figuring things out with
No.
blocks.
Right.
Well, of course not. I mean, that's what you do when you're learning. When you apply something you already know, that's a different thing. And sometimes I think we skip the learning part and sort of just go into applying. But I wanted to go back and talk about representations, because what we start with in the sort of the middle part of this, after noticing and articulating, is we actually have people represent specific examples.
Okay.
So we're not talking about building a general proof yet. We're just sort of saying, what does it look like? Can you tell a story situation? And so the one I was talking about, it was having some cookies on a tray, maybe cookies on a tray, and if I put one cookie from one tray onto the other, I have the same number of cookies. So that supports the idea of 19 plus 6 is the same as 20 plus 5, which is a really good computational strategy.
Yes.
But you don't want it to be a single entity that maybe some kid thought of on some problem. And by doing this kind of analysis and naming it, then that strategy can be something that kids can count on and use consistently, because they know it's about addition. And they say, oh, I know in addition I can move something from one addend to the other and get the right answer.
Still have the same value.
But after representing specific examples, we, again, after 3-4 of these 10-15-minute sessions where that's the nature of the work, it moves into actually making an argument that it works for all numbers. Now, when I say all numbers, it has to be modified. It's sort of all the numbers that the students might know about.
Sure.
Second graders, there's a lot of numbers that in our world that they may not know about.
Maybe not getting into decimals just yet.
And, yeah, and so when they make an argument, it's for the numbers that they know about.
Okay.
And in fact, some kids are suspicious a little bit about, how can you say this is true for all numbers when I know numbers keep going on, and there might be numbers in the world I don't understand yet. And so we build these arguments, but that's not the main goal. The main goal is understanding the nature of the operations.
Okay.
And that you see lots of students will say, it really doesn't matter how many cubes I have. And so they're not using variables like x's and y's the way they will older students might make formal arguments, but the mathematical reasoning is the same. It's just that they're using stories or cubes to make their point.
So they're not so caught, what we want to happen is to not be so caught up in these specific numbers, but in this underlying idea or property that if you move it around, it doesn't matter.
Yeah, and when I started this, I was saying I think representations are somehow misunderstood. I think a big part of it is that people still associate these as somehow crutches for people who can't do the numbers, as opposed to, these are tools for reasoning.
Sure.
And once we have an image like those cubes moving back and forth between the two trays, my head, I can imagine that with fractions and decimals and things that couldn't be represented by whole blocks. And I think that we misunderstand, and it's not an accident that the word see means both see visually and understand.
Sure.
And so one part of the goal here is to be helping students think about the real meaning of the operations. And so I've been talking a lot about addition in my examples. And so another phase in this teaching model that's in this book and the lesson sequences are built around is comparing operations. Because once students find out something is true, they tend to think it's true about number and don't realize the significance of the operations. So one of the things that we might ask them, for instance, one of the lesson sequences starts with what happens if you add 1 to one of the addends. So if I'm adding these two, if I add these, I get 6, but what happens if instead of adding 2 and 4, I add 3 and 4? And so it's pretty easy with the cubes to see if I add 1 to an addend, I add 1 to the sum.
Sure.
And so that becomes something that students might notice, articulate, represent, and make an argument for. But then we ask older students, maybe third grade, what happens if you add 1 to a factor?
Oh, right.
And they usually will say immediately the same thing, that it changes the sum by 1. And after they look at a few examples, they begin to think, wait a minute, what's going on here?
Right.
And so this is where, again, the power of a diagram or a story.
Mm-hmm.
So if I think about adding 2 plus 4 and comparing it to what happens if I have 2 times 4, if I have 2 bags with 4 apples in each bag, that's a nice image for multiplication.
Sure.
But then if I add 1 to the 2, I'm adding a whole bag.
Another bag.
And so you're adding 4 to the sum.
Yes, you are.
And so having that image, because it's kind of weird if you look at it with numbers, why do you change the product by the one that isn't changed, right? If you look at 2 times 4
Yes.
and 3 times 4, we're changing from 8 to 12, but it's the 2 that change. And so if you look at it as just numbers, it's a puzzlement. It really doesn't make sense until you have the meaning of multiplication.
Right.
So if you've got these bags or cubes or an array, some image in your head, it's pretty easy to see why when you change 2 bags of 4 apples to 3 bags of 4 apples,
Yes.
you have 4 more apples.
So, yes, I agree with you. That is easier to see when you have a visual representation. I don't know, when I was in the classroom, I don't know how I would have taught math without tools. And even now when I'm working with teachers, I bring out the tools. Something that keeps happening, though, in different schools and places where I am, is that teachers will, not all teachers, some, may pull out the tools for a day or 2 and then put them away.
Right.
Or even in some districts, they might say they're a crutch.
Yeah.
We show them on day 1 and then they go.
Right.
But I don't know that that's enough time to build a mental representation
Absolutely.
for most kids.
I think the whole point to me of doing the things with the cubes and the diagrams is you reach a point where you don't have to do it anymore. It's in your head. So I told you a story about my son and daughter. I can tell you a story about my grandson who's 6. And he was at my house for Thanksgiving. And when your mother's a math teacher, or your grandmother, you never know what might be. But he was getting bored with what he was doing, so I gave him a number chart and a tens, a hundreds chart.
Okay.
And I said, why don't you color in all the ones that have 3s in them?
Mm-hmm.
And he did, and then he came back and he was really distressed because he said, this is nice, but this one goes with a bump.
Okay.
Because the 30 is in the line of the 20s.
Gotcha.
So, I wasn't going to go to him on why this is constructed this way, but I said, why don't you try the 5s and see what happens? And he came back, and this time he said the same thing, only he was happy because he wanted it to be regular.
A pattern.
And so now it was regular, it just wasn't the pattern that he had thought.
Okay.
So then I said to him, well, why don't you do the ones that are 6s? And he started to go away, and he came back, and he goes, same thing.
Right.
And so, to me, that transition,
Yes.
that he did it a couple of times, physically doing it out, and this was a pretty simple pattern to notice.
Sure.
And so after doing it twice, he could then do it in his head.
Right. Kids
And-
build themselves off of the
And
tools,
that's
right?
what we want this to be. You do it with the tools until it's like so boring because it's just obvious. But what's obvious is the structure. It's really about math practice. It's an 8 or 7. I always mix up with
I do
the
too.
one about
That's
structure.
Right.
One about structure. And so you begin to notice the underlying structure, and that's really what the operations are about. It's not the numbers. And so it controls how the numbers work. And so you talked earlier about number sense, but one of our teachers formed the phrase, I haven't paid enough attention to operation sense. Do kids really know the difference between adding and multiplying?
Nice.
And I remember thinking, so because we're here, you haven't seen my handwriting, which isn't particularly good. I do not have that nice elementary handwriting. So if I was writing 3 plus 5 or 3 times 5, they might look alike.
Sure.
And they actually even look alike printed where it's neat. But the mental image you want people to have about what does 3 plus 5 look like as compared to 3 times 5, that's not going to get generated by just numbers on a page. You've got to have a diagram, a story, some cubes in order to sort of see adding 3 apples to 5 apples is very different than multiplying 3 bags with 5 apples in each. And kids need that.
I agree.
And so I'm giving really small numbers, but they need that to move into making sense of fractions, decimals,
Right.
and algebraic
Make
symbols.
those generalizations to other
Otherwise,
numbers.
by the time you're up in algebra, you're just manipulating the symbols using your memory,
Right.
which is not the strongest part of the human brain.
I'm a huge advocate of tools, and I think kids wean themselves off. And something I argue for is if you're in a classroom and kids are using tools, they need the tools,
Yeah.
right? They haven't been able to quite make that visual representation yet.
And one of the things that we found is that it's a challenge to some of the students who get answers fast without thinking, and that to ask them, how could you show that?
Right.
How would you show that to someone a year younger than you?
Right.
How
Right.
can you make a picture to show your reasoning? It's not obvious. So the
No.
very kid who might have some number facts very quickly
Yes.
is still impoverished in some way if they don't have this kind of picture. And the challenge of having everybody in the class needing to do this gives everybody a challenge, whether they're students who haven't succeeded in the past or whether they're students who, according to at least knowing answers fast,
Right.
have looked to be successful. It fills in something for their background.
Right. It makes a whole picture, a complete picture.
Absolutely.
I can remember talking to a few students now, and I use this over and over, the ones who don't want to use tools or draw pictures, they just want to tell you the answer. And what I say to them, because I feel like there's a lot of confidence that they've built around their math abilities.
Right.
And so what I say to them in order to get through to them, why it's important is like, you know, you might be an engineer one day, you might run a company and be a designer, and you might go on a vacation or go to a meeting, you need something built or designed. You've got to be able to make sure that your explanation or your model is clear enough for them to follow through on that design.
Yeah.
Right? We need
That's
the whole
nice.
picture. Yeah. So they seem to say, okay, I can see the purpose behind
Yeah.
it, I'll do it now.
Yeah,
Right.
well, the thing is, no matter how good your ideas are, if you can't explain them to somebody else, they're useless.
Right. I was watching
It's
true. I was watching a biography though on Elon Musk, right? Tesla,
Right.
SpaceX. And he was in the process of designing the Tesla, but he needed to go to a different company to get the money. And so he couldn't just say it. He had to
Yeah.
explain it and show it. So again, it helps you, I think, now in the classroom and later on in life, if you can explain it and understand it and share with others, definitely.
And the other thing that we haven't actually mentioned is that the kids actually like doing
They do.
this. And so in one of the classes, one of the stories in which I'm not sure which book it's in,
Mhm.
there was a class that had been working on this add one to an add end and the sum remains. No, actually, add one to an add end and subtract one from the other, and the sum remains the same.
Okay.
And they were really confident in what they had done. And the teacher asked them, does it work for subtraction?
Ooh.
And they were shocked
Right.
that the same rule didn't work for subtraction. And then the teacher said, well, why don't we do the same thing? Let's start with some
Right.
examples
Okay.
and see if we can build a new rule. Well, at the end of the year, this teacher has a habit of spending some time at the end of the school year asking her students what they remember about the year.
Mhm.
And one of the little girls in this third grade class said, do you remember the time we found a rule for addition didn't work for subtraction and we were without hope? I'm so happy we found a rule for subtraction. But it was really emotional. I mean,
Sure.
she was really expressing, oh my goodness, something I thought was true is not true, but something else is.
Right.
But it was really about comparing operations,
Mhm.
which is the final part of our teaching model. So it starts with noticing,
Okay.
moves to articulating, representing specific examples, making an argument for the general case. And again, I have to say general sort of depends on the age you have,
Sure.
how many numbers. Lots of arguments you make have to be changed when you realize there are numbers less than one.
Yeah. Okay,
And
yes.
so the property may still be true, the conjecture may still be true, but the argument that you gave based on cubes might need to be modified.
Yes.
And so that sort of moves kids from using arrays, which work for whole numbers, to thinking about an open array and eventually an area model where they have more flexibility and the one side of the rectangle might not be a whole number.
Okay.
But that the argument then has to be modified. And then after making arguments, we look at this comparing operations and sort of like, does the same thing true? How is it different for addition and subtraction or
Sure.
addition and multiplication?
So it creates this process for kids to dig in, investigate, and learn more,
Right.
and really sets the stage for perseverance. Right?
Well, yeah.
I think so.
I mean, it sort of says, here's a problem. So some of our lesson sequences are designed for a whole half year where they're looking at maybe two ideas, something about addition and something about multiplication. But it gives them a chance to participate in the real mathematical practice of making an argument and asking this question, but why does it work? How is it always true?
Mm-hmm.
And that's a pretty amazing experience.
I think you
And
can.
one that people ought to have.
I agree.
Why
I
should
agree.
only a few people get to have that?
I agree, but I think when people like you have these great ideas, you share them with teachers who are willing to do this work and
Right.
try to get messy, and then you write books like this one. I think it's definitely an
tell
opportunity
you,
for us all to learn. So
I have to
appreciate
say,
that.
one of the fun things
Okay,
about
please
this
tell
book
me.
is that we have not just print cases, but video cases.
Oh, cool.
And
Okay.
if you just once you have the book, if you
Right.
hold this up to your smartphone,
Uh-huh.
you see a teacher doing the work that you're trying to do.
Oh, and then it's not
Real
a guessing
teachers,
game,
real
it's a real
Yeah.
world example. I love it.
Yeah.
So I love talking with you, Virginia.
This
I
was
really
really,
do.
this
Right,
was
it's
really
love.
good. One of the
Yes.
things I wanted to say before we
Please
left
do.
is that I am going to be speaking at the Palm Springs Convention.
The California Mathematics Convention.
Yes, the one in
South.
Palm Springs.
Okay.
And I'm also going to be speaking at the California Mathematical Convention North in the Silmar.
Okay.
And that the recent edition of The Communicator has an article that summarizes a lot of these ideas.
And that's a September 2017
Yes.
article. Oh, I can't wait.
And I love talking to teachers about these ideas. My
Yes.
email is there.
Good.
And I had a lot of teachers that I knew really and worked with over the years in Massachusetts.
Yeah.
And when I moved out here, I gained proximity to my grandson, which is really important to me, and
Yes.
my son and daughter. But I sort of don't have a group of teachers anymore.
Okay.
So
We're gonna get you some.
I'm really interested. I'm really interested in helping people think about these ideas.
That's exciting. I'm really excited. And so we're going to put all of Virginia's information on the website so you can email her and ask her questions. In the meantime, these are just some of the books. You co-authored quite a few.
Yeah, there's another whole
Right.
series called Developing Mathematical Ideas.
I love
People
it.
can check that out.
Okay.
And there's a reference to it in the
Communicator?
In the Communicator.
Okay. So again, you're going to be in Palm Springs. I think it's late October or
Yes.
November. And then
October.
Asilomar up
It's in
north.
December.
December.
Yeah, and I love to talk to people. I'm very approachable.
You are.
So please come up and talk to me.
Good. Thank you for coming, Virginia.
This
It's
was
been a
great.
pleasure. Thank you.
Thank you. So nice to meet you.